63,376 years. Did you know that if we could travel to each galaxy in 1 second, it would take us 63,376 years to visit just the 2 trillion galaxies in the observable universe? 2 trillion galaxies. Scientists believe that the observable universe is only 5% of the whole universe. Our own Milky Way galaxy has 400 billion Milky Way galaxy stars, and it takes light thousands of years to travel from one galaxy to another. What's even more astonishing is that the universe is expanding in all directions at a speed faster than the speed of light. Famous physicist Brian Cox recently said that the universe is so vast that we can't even imagine it. This is the picture that Hubble took, and you see that it's anything but empty. It's called the Hubble Deep Field Image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of lighting, and virtually every one of them, over 10,000 of them, are actually galaxies. Distant galaxies, so they're not stars, they're galaxies. Now, those galaxies on average have 100,000 million stars like our Sun in them at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image is 13.2 thousand million light-years away. Now light travels at 300,000 kilometers per second, 186,000 miles a second, and at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began their journey to us before there was an Earth. And for some of the most distant galaxies they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the Sun and the planets and moons of the solar system. So imagine what that looks like. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy with 100 billion stars like our Sun in it at least. There you see that the structure in they're not randomly distributed. It's very interesting. We're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, that's the 1 billion light-year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. This is the number of stars we know from observation or in the observable universe at the moment, 30,000 million stars just like our Sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. So how big is our universe? Is it infinite or does it have an edge? What is its ultimate fate? What existed before the Big Bang and what lies beyond it? Let's dive in to find out. To begin, the fact that we can determine the observable universe's size to be 93 billion light-years across is truly astonishing. But how do we come up with this? The story starts with an Australian mathematician and physicist named Christian Doppler who lived in the 19th century. Doppler was trying to explain a peculiar phenomenon related to electromagnetic waves. When an observer moves closer to the source of a wave, the length of that wave decreases, and if they move away, it increases. We now call this the Doppler effect, and Doppler effect it applies to all types of waves. To understand this better, imagine you're standing on a sidewalk watching cars drive by. As each car approaches you, the sound of its engine appears higher in pitch. However, as the car moves away from you, the sound gradually becomes lower in pitch. This is the Doppler effect in action. For astronomers, the Doppler effect is crucial. By using stars as reference points, they can detect anomalies in the wavelengths they observe. If the wavelengths are increasing, it means the object is moving away, resulting in a red shift. Conversely, if the wavelengths are decreasing, it indicates the object is moving toward us, resulting in a blue shift. Fast forward to the 1920s when Edwin Hubble made a significant discovery. He observed that some objects in the universe were moving toward each other while others were moving away. In a broader sense, it appeared that everything was moving away from everything else. Hubble's revelation was groundbreaking, shifting the prevailing view of a fixed and stable universe. What's more, this universal expansion seemed to be accelerating. Although we still don't fully understand why or how this expansion occurs, subsequent measurements have confirmed and refined this concept. Dark matter and dark energy are the leading explanations for these observations. The study of redshift is fundamental for understanding cosmic distances, especially for objects that are incredibly far away. However, things become a bit tricky when dealing with vast cosmic distances. For example, if you're observing something 1 light-year away, you're essentially seeing it as it was 1 year ago. But during that year, the universe has expanded, increasing the distance between you and that object beyond 1 light-year. Astronomical observations have estimated the age of the universe to be around 13.7 billion years. 13.7 billion years. One of the most distant objects we've detected is a galaxy called GNZ11 or GNZ11, which is 13.4 billion years old, 13.4 billion years old, nearly as old as they come. However, despite the light from this galaxy reaching us from 13.4 billion years ago, it now lies much farther away than 13.4 billion light-years. In fact, astronomers believe it's a staggering 32 billion light-years from Earth, so it's essential to recognize that the universe's age in years doesn't directly correspond to its size in light-years. But we can go even further back in time. We can detect photons that existed before any stars or galaxies formed. These ancient photons originate from the cosmic microwave background known as CMBR, a faint radiation filling all of CMBR space. This radiation represents the earliest known electromagnetic radiation and is, as far as we can tell, the oldest phenomenon we can detect. When it comes to understanding the cosmic microwave background radiation, one of the most accurate sources of information is the Wilkinson Microwave Anisotropy Probe, or WMAP. It, along with other estimates, has revealed that the farthest observable photons we can detect originate from a staggering 46.5 billion light-years away. This suggests that our observable universe extends to a minimum of 93 billion light-years across, equally in both directions. As for Earth's location within the broader universe, we don't have a precise understanding, and there's no compelling reason to believe that we occupy a special or central position. In any case, the observable universe is estimated to be approximately 93 billion light-years in size. However, this raises the intriguing question, what about the entirety of the universe? Is it infinite in extent? The straightforward answer is that we simply don't know. Anything beyond the observable universe lies beyond our capacity to observe, making it impossible to provide a definitive answer. Nevertheless, we can make educated guesses based on various studies attempting to calculate the universe's true size. For example, one statistical estimate carried out by researchers at Oxford suggests that the universe might be 251 times larger than the observable 251 times larger universe. This would equate to a vast expanse measuring 23,343 billion light-years, 23,343 billion light-years across, and that's a conservative estimate. In another study, it's proposed that the universe spans a mind-boggling 10 to the power of 10 to the power of 10 to the power of 122 megaparsecs in size, with 1 megaparsec equals 3.26 million light-years, 1 megaparsec being equivalent to 3.26 million light-years. This number is so astronomically vast that it defies reasonable units of measurement. If the universe truly encompasses such immense dimensions, even if it's not technically infinite, it would be practically infinite from our perspective. Nothing from our location could ever reach its supposed edge, nor could anything from the edge reach us. But here's where things get even stranger. Remember, we inhabit an expanding universe, a fact initially observed by Hubble, albeit with some errors in his initial measurements. More recent studies have converged on an expansion rate of roughly 70 km per megaparsec. In practical terms, this means that an object located 1 megaparsec away from us is receding at a rate of 70 km per second. If it's 2 megaparsecs away, the recession speed doubles to 140 km per second, and so on, making the universe's dynamics even more intriguing. To put it in simple terms, we often say that the observable universe is about 93 billion light-years wide, which is equivalent to 28,500 megaparsecs. Now, if we consider the points that are the farthest away, they appear to be moving away at astonishing speed of approximately 2 million kilometers per 2 million kilometers per second. That's almost 10 times faster than the speed of light, and according to Einstein's theory of special relativity, nothing can exceed the speed of light. So what's happening here? Well, it's not as if the universe itself is zooming away at 2 million kilometers per second. Instead, it's the space between objects that's expanding at this rate. To understand this, we turn to Einstein's theory of general relativity, which general relativity theory handles these cosmic conundrums. His theory provides a different perspective on speed limits in the universe and allows for the mind-boggling idea that the universe's expansion can seemingly defy the speed of light without contradicting the principles of special relativity. What we understand from this is that the universe isn't really stretching into some sort of void, but rather space itself is expanding, creating more distance between celestial objects. This notion is mind-boggling but has been well supported by various cosmological observations and theoretical work. One implication of this is that there are regions of the universe from which light will never reach us. As the universe expands, certain regions move away from us faster than the speed of light, rendering them forever unreachable. This fascinating phenomenon suggests that there are parts of the universe that, while they exist, will forever remain beyond our observational capacity, hidden behind a horizon defined by the universe's expansion. What's more, there are galaxies that have now moved so far away that we may never see them again. These galaxies are essentially traveling faster than the speed of light in terms of their relative motion due to the expansion of space itself. These galaxies are slipping beyond a cosmological horizon from which their light will never be able to catch up with the expanding universe, leading to an ever-growing number of galaxies that become permanently hidden from our view. When we combine all this knowledge, it leads us to a profound conclusion: our universe is both incredibly vast and mysterious. From its birth in the Big Bang to its ongoing expansion, the universe continues to surprise and challenge our understanding. Despite our advances in cosmology, there remains much we do not know and perhaps may never fully grasp. For instance, what exactly triggered the Big Bang? What existed before it? These are questions that continue to puzzle scientists and inspire ongoing research. Additionally, the concept of dark matter and dark energy remains one of the greatest enigmas in cosmology. We know they exist due to their gravitational effects, yet their exact nature eludes us. Dark matter and dark energy together comprise about 95% of the universe's total mass energy content, leaving us to wonder about the true composition of the cosmos. Despite these uncertainties, what we do know is nothing short of awe-inspiring. Our universe is a vast and dynamic place filled with wonders that stretch our imagination and challenge our scientific prowess. As we continue to explore and learn, each discovery brings us one step closer to understanding the grand tapestry of existence.